Does it say record?
Yeah,
All right,
it does.
very good.
Start the timer.
Alrighty, if you would, Emily Keene, do we know final velocity in this problem?
That's what we're trying to find.
Alright, so we need to have it in the equation. Do we know distance?
Yes.
We do. And let's put a check there. Do we know the acceleration?
Yes.
Because we're in free fall, the acceleration is the acceleration constant. So yes, we do. And do we know time? No. And initial velocity.
Yes.
Yeah, we do know. When something is dropped, what is its initial velocity just for a
Zero.
second?
Zero.
Right. So even when you watch this really close, you'll see it hover for an instant. You didn't see it, but it is for just an instant of an instant. It is 0 in free fall. So we have to come to the problem knowing that. All right. So then, Emily, recalling, I don't have the equations in front of you now, but we want to get to the point where we don't need to look at them. Can you remember which one did not have time in it?
The second one?
All right, and that is, do you call it? The very worst squall, which we might have a worst squall coming through on Sunday.
Yes,
The first squall, and it comes with 2 axes. All right, so hopefully that's not true for us on Sunday.
I don't think so.
Now they're saying it's bending to the
I hope
east.
we aren't off schools Monday.
Yeah, but may not now.
We have our
It
senior
was
game.
looking like it was coming right here, and now we'll still get plenty of rain and wind, so we still might lose power and have trees down. And
Enough to have in school,
Game.
but not enough to kill us, so I
It's
mean,
a little different than a
it's a
straight
win-win for
on
everybody.
hit. All right, if you would, before I do, write down this equation and put in the appropriate numbers where they go. We're looking for V. We're looking for the very last V, the final velocity. All right, plug them in and chug it out. Plug and chug. Are you doing it, Brian?
Yeah.
Okay.
Because we're in kilometers.
So we can change this.
Wait, so there's just compare kilometers to meters. 1 kilometer equals 1,000 meters. That'll just be.
All right, look at the numbers where I put them. Did you put them in similarly? I made one mistake. I put a star where I made the mistake. Does anyone know what the mistake was that I did? I did change it to meters, so I did do that right, but what did I fail to do?
4,800 feet. Wait, that would be
What?
9,000.
What did I do wrong when I plugged it in? When you do distance and it goes down, you have to use a minus sign. So, little training on these problems. The 150 went downward, so it is negative. Which is, we wanted a velocity that's positive, so, because we have to take the square root, so we don't want a negative on the right side. Alright. I need someone to multiply negative 9.8, negative 150. Remember, I switched it from kilometers to meters, so I'm dealing with 150. I need the square root of that number. And because I'm always using 9.8, it's 2 sig figs. So, you got that going there, anyone? 54, anyone confirm?
Yeah.
54, and that will be a velocity, so it'll be meters per second. All right, so easy peasy for these dropping problems. Because velocity initial is always 0, the acceleration is always known, and you pick up the rest of the numbers from the problem. All right? Before we break for some other activities today, I want to take a note about throwing upward. So if you would draw this little scenario. There's a hand, I put a ball this time. I'm getting really creative. And you can put any object there that you're throwing upward. And it has an initial velocity when it comes off my hand of 3.5 meters per second. And when it goes up, it's going to reach a peak and come back down. Notice my dotted lines went up and went a little bit over and down. It really goes up and comes straight down. But I'm drawing it this way so I can talk about the velocity at certain points. So draw something being tossed upward. And we'll do one of those as soon as you get that drawing down and we get the training we need. When you're tossing an object upward, and for example, the velocity is 3.5 meters per second going up, at the very top, the velocity zeroes out for an instant when it's changing directions. So at the top, right, velocity is 0. And then when it comes back down, when it reaches the same point just before it hits my hand, as when it was going up was 3.5 meters per second, guess what the velocity is when it comes back down? It's negative, so it's going downward, so it's the same. That is neglecting any other forces, such as the friction due to air resistance.
If we had time, we would be able to figure out deceleration as it was going upward and acceleration as it was going downward.
Yeah. Yep. All right. So that's about all the training you need to do one of these problems. So we're going to sketch another one. Let's do a gun. Anyone ever shot a gun?
Yeah, I started shooting last week.
I have to.
I shot a Nerf gun.
Yeah.
All right. So this time, what's being tossed upward is a bullet. So draw this scenario. And the velocity coming out of the gun is 101 meters per second. So the initial velocity, I'm going to put V sub O here, is 101. Velocity at time 0. And can I just stop there and give you that one measly little information and say find the max height? Could it be that we know enough to answer that question? Let's see if we can amaze even ourselves.
Yes, we can figure that out.
VXA T and V sub O. 1, 2, 3, 4, 5. All right, Alex, do we know do you have the drawing yet? Oh, wait a second.
My drawing is really bad.
That's okay.
Me too.
There's no gun
doesn't really
in
go
this
like
room that looks worse than
It
that.
Sock.
looks like a wooden gun. Like
Sock.
21 wooden guns. It was like.
All right, Alex, do we know the final velocity when it comes
Yes.
back down? We do, because we knew what it went when it went up. Do we know the distance that it's going?
No.
But we are asked to find the maximum height.
So
That's a
what we're finding, so we
distance.
circle that.
Yep. Do we know the acceleration?
Yes, we do.
Because it's in free fall. Yeah, this is going up and down vertically. That's in free fall. Do we know the time?
No.
Do we know initial velocity?
Yes.
All right. So, one equation that we learned does not have time in it. Again,
Let's use the last one then.
all right, the
BO
same.
squared plus
Right.
2AX.
Right. The only thing that I have to train you with on this is the equation won't work if we're going to put in the velocity and final as I trained you over there, negative 101. It's not going to work. It's not going to get us what we need to know because we want to know what the maximum height is. So I'm going to end the problem right here. This is the end of the problem. So I'm going to make my velocity final up here. So it's true what Alex said that we do know the velocity final down here, but since we're asking for the maximum height, we need to know what it is up there. If we did this equation with the velocity final down here, the maximum height would not be answered. We would get the height of 0 if we did that. So we don't care about what the height is when the problem is over. We want to know the maximum height and that right there. So I'm going to end the problem there and call that velocity final. So a little bit of training in there. So Alex, what is velocity at the very top?
0.
Right, because this first second, it's got to change directions, and so we get that. Then the initial velocity I gave was 101. Acceleration, negative 9.8, and x is what we're looking for. So, mathematicians, I need someone to square 101. Zach, what's 101?
10,201.
I'm sorry?
10,201.
All right. And 9.8 times 2 is what? Negative
19.6.
19.6. All right. And so if you take, I'm trying to figure out why it's going to come out negative.
It won't. Because when you
Oh yeah, I moved this over. That's why it will come out negative. All right, so I moved the 101 squared over to here. I failed to put in the negative sign. All right, Zach. So divide 10,201 by 19.6, and what do we get?
520.
520 with 6 figs. We're only allowed 2, so that is 2, and that is a distance, so it will be in meters. So, have you amazed yourselves that you can take from one piece of data, find the maximum height that this went? So, it is quite amazing. All right then, I think that'll get you through your problems that you're going to do later, those 2 examples. One for throwing upward and one for dropping. Those principles will follow you.
Can we stop?
All right. No. All right, what time? Did we start it again?
It's almost at 12 now.
Okay, yeah, stop. All right, and just leave it off for a second.